Welcome to the course on biostatistics and design of experiments. In this class we will talk about F distribution, Ftest. So far we talked about T distribution and comparing means. In the Ftest we compare something called variances. Variances are nothing but the spreads. Okay. So here in Ftest or there is another test called analysis of variance, we are comparing variances. Okay. This is valid for normal and non-normal distribution data set also. So when you are comparing variances, the null hypothesis will be sigma 1 square is equal to sigma 2 square and so on, where sigma is your standard deviation of the population. So sigma 1 square will be the variances. Okay. We cannot reject the null hypothesis if p is greater than 0.05, and the alternate hypothesis will be sigma 1 square or sigma a square is not equal to sigma b square and so on accepted. Okay. So here when p is less than 0.5 we will reject null hypothesis and we will accept the alternate hypothesis. So that is what variance comparison is. So the advantage of this variance comparison is it tells you about the spread of the data. That means what are the repeatability of the data. Suppose I take an instrument and I take a sample and then I do it 10 times. I will get some variations or variance. Okay. Now is this variance too much or too little? If I use another instrument and I do the same sample 10 times, I will get again another set of variance. Okay. Is these variances are very large or very small, acceptable? So here the Ftest is very useful. I am comparing two operators. For example, I have a very well trained operator and I have a newly joined operator. I want to see what is the consistency of the results they produce. So I can test the quality of the newly joined operator with respect to the operator who has been there for a very long time, and I compare variances and I say yes, the variations that the newly joined operator produces is comparable to the variations of the expert. So if a newly joined operator comes in, you give him a training and then we will give him a few samples and ask him to repeat, and then we will compare it with the variations of the results from the expert, and then we will conclude yes, this newly joined operator is well trained and the variations he produces are not very large, it is comparable to the expert. So that in those situations, for comparing instruments repeatability, for comparing the variations operators produce, comparing variations produced in one lab versus another lab, especially this is very useful when you are performing clinical trials. So all these situations we use Ftest. Also suppose for a 2 sample t test I should have only 2 samples. If I want to compare sample A with sample B, sample 1 with sample 2. Suppose I have 3 samples. For example, if I am comparing 3 drugs or 2 drugs with a control or 1 drug with a control and a placebo. Okay. So I have more than 2 sets of samples. I might not be able to do 2 sample t test. Of course I can take 2 sets of samples at a time and do a t test, but if I want to go at one single shot comparing the data of these 3 sets, what do? I look at the variances or the variations, and there comes something called the Ftest. So I can use the concept of analysis of variance and then I say that sigma 1 square is equal to sigma 2 square is equal to sigma 3 square. That means sigma square of the control is equal to sigma square of the placebo is equal to sigma square of the drug. That is the null hypothesis. Alternate hypothesis, one of them could be different. Okay. So in such situations again comparing variances are very good, very useful instead of using 2 sample t test for different combinations. Okay. So what is Ftest? So the H naught here in an Ftest is standard deviation of population 1 is equal to the standard deviation of population 2, or actually we should not use standard deviation, we should use variances, because variances are additive whereas standard deviations are not additive. Why? Because you take a square root of the variance to arrive at the standard deviation. So obviously it is a non-linear. So non-linear cannot be additive, whereas variances are additive. Okay. So the null hypothesis in an Ftest is sigma 1 square is equal to sigma 2 square. Obviously the alternate hypothesis could be sigma 1 square is not equal to sigma 2 square. Okay. So, we calculate something called a F ratio, where F could be S1 square, that is variance of sample 1 divided by the variance of sample 2, and then of course again we go to the table. There is a F table, okay. There is a F table which says whether the calculated F value is greater than the table value or it is less than the table value. Okay. If the calculated F value is less than the table value, we will accept the H naught. Okay. If the calculated F value is greater than the table F value, we will reject the H naught and accept the alternate hypothesis. Now, there will be 2 degrees of freedom, because S1 will have one set of degrees of freedom, S2 also will have its own set of degrees of freedom. Okay. So, this table has interestingly row wise and column wise data representing both the degrees of freedom. So, degrees of freedom for S1 will be N1 minus 1, degrees of freedom for S2 will be N2 minus 1. Okay, let me show you the table here. Okay. So, you have the table, F table for P is equal to 0.05, that means 95% confidence interval. So, degrees of freedom for the numerator, degrees of freedom for the denominator. So, if you want numerator more than 10, you go to the next page. Here I am showing this, right. So, it goes up to 20. So, degrees of freedom for the denominator is here, goes up to 30. So, this is for P equal to 0.05. Similarly, we can have for 0.01 also. Okay. The degrees of freedom for the numerator, degrees of freedom for the denominator, going like this. Okay. So, this table is very useful, and of course, Excel also can calculate these values. So, I will show you how to do that, but manually if you are doing, we can use these tables, especially the book I mentioned in the reference called Fisher, that gives you that data. So, we can use the F table to calculate the F value. Okay, let us go slightly more into the fundamentals. We need to know what is F distribution. Okay, what is F distribution? This is called a Fisher and Snedkor distribution. So, it generally looks like this. Okay. So, at different values of degrees of freedom, it will look like this. It is a continuous probability distribution. Okay. It is a right skewed, because on the right hand side it is skewed. It is not like a normal distribution going up and coming down like a bell shaped, but there is a skew. It has a minimum of 0, but there is no maximum. So, it can be up and up. If for very low values of degrees of freedom, it can go right up very high. Okay. And it is only positive, there is no negative. This data is used, very useful if you are doing a Ftest, that means if you are comparing variances of 2 sample test, 2 sample, and if you are doing an analysis of variance. So, we do that actually. So, as I said, the null hypothesis will be the variances of the 2 populations are equal. Alternate hypothesis for a 2 tail could be the variances are different. Single tail hypothesis could be variance of sample 1 is greater than variance of sample 2, or the variance of sample 1 is less than variance of sample 2. Okay. So, we can do in the same fashion. So, this is called an F distribution. It is skewed like this, as you can see here. Okay. Okay. So, Ftest, as I said, okay, it tries to identify the model. It can be used for fitting the data. Suppose I am doing a regression analysis, it tells you I can find out what is the error sum of squares. Error sum of squares means data that is not fitted to the model as against the total data. Okay. So, that way Ftest is very powerful. It is used in many situations actually, and also we can use it if you are comparing as I said instruments, if you are comparing operators, if you are comparing more than 2 sets of samples for the population, and so on actually. So, if I take 2 random samples of size n1 and n2, and each of these has a variance of s1 square and s2 square, and they are from the normal population. Okay, and the population variances are sigma 1 square by sigma 2 square, then the F is actually given by s1 square by sigma 1 square divided by s2 square by sigma 2 square, and the F distribution will have 2 degrees of freedom, n1 minus 1, n2 minus 1. So, n1 minus 1 relates to the numerator sample, n2 minus 1 relates to the denominator sample. So, you have to remember that. So, you can sometimes have different F values also. If I take the numerator as the denominator as the numerator, but when I read out from the table, I will read out in a different way. okay. So, I will show you an example later. So, okay. So, for example, I am looking at 7 women from a population and 12 men from a population, they are tested for something, blood glucose for example. So, it shows you the standard deviation of the blood glucose in each sample and in each population, okay. So, this gives you the standard deviation of the population, this gives the standard deviation of the sample, okay. Here I have taken 7 women and here I have taken 12 women, these are the samples, these are the population, standard deviation from the, okay, some sort of a mean, and okay. So, what do you do? F is equal to S1 square by sigma 1 square, okay. So, that means S1 square divided by sigma 1 square divided by S2 square divided by sigma 2 square, okay. So, we can have 35 square by 30 square divided by 45 square by 50 square. So, I get 1.68, that is the F, okay. Now, the degrees of freedom is numerator is 7 minus 1 6, denominator 12 minus 1 11. So, under 6 and 11 for 95% confidence, under 6 and 11 for 95 I get 3.09, okay. So, I put it as 3.09. Now, notice instead of putting women on top here, I can also put men on top then women at the bottom. So, it can be 45 square by 50 square, 35 square by 30 square. So, I will get a different F value, note that. Now, the F value is 0.595, but then I should look under numerator degrees of freedom is 11 and 6. Did you notice that? I can put numerator as denominator or denominator as numerator, but when I look into the table, I look at the corresponding DF in a proper way. So, here I look 11 and 6 instead of 6 and 11. So, 11 and 6, if I go to the table, so 11 and 6 is next page, so it is 4.03, you understand. So, we get 4.03. So, if I had taken men variance on the top and women variance on the bottom, the degrees of freedom is 11 and 6. So, I will get an F of 4.03. If I put women variance on the top and men variance at the bottom, I will get 6 and 11, for the F table is 3.09. So, I compare 3.09 with 1.68, so I cannot reject the null hypothesis because the F calculated is lower than the table F. And if I put the men variance on the top, then I will get 0.595, this is the calculated F value and the table F value is 4.03. So, I cannot reject the null hypothesis. So, either way I cannot reject the null hypothesis. So, you need to see this, you are doing a ratio calculation. So, instead of numerator you can have denominator, denominator can be numerator, but when you select the degrees of freedom you should correspondingly change it, and this table as you can see, this gives you the numerator degrees of freedom, this gives you the denominator degrees of freedom, as you can see that, okay. So, you have to use properly the degrees of freedom. So, in either way here in this particular problem we see that you cannot reject the null hypothesis because your table F value is much larger than your calculated F value for 95% confidence limit, okay. Either way, whether we put the variance of the men in the numerator and variance of the women in the denominator, or if I put the variance of the women in the numerator, variance of the denominator in the bottom, okay. So, this table is very useful, be it 95% confidence interval or be it 99% confidence interval, okay. So, Ftest looks at 2 population variances and determine if there is a significant difference between the 2 populations, okay. So, if I am taking only samples, I do not have any idea about my population. So, x bar will be, as you know, summation of all the x's divided by n, and for other data set it will be y summation of y by n2, and you know how to calculate the standard deviation, right, x1 minus x bar square summation divided by n1 minus 1, standard deviation of that, the other one is y1 minus y bar square summation divided by n2 minus 1. So, f will be S1 square by S2 square, and then you look at F distribution, n1 minus 1 as the numerator, that means that will be on the column, n2 minus 1 as the denominator, that will be on the row. So, do not forget that. Whereas, if I do F is equal to S2 square by S1 square, then I will look at n2 minus 1 as the column and n1 minus 1 as the row, do not forget that, So, we can have either one tail test or a two tail test. Of course, it is good that the data follows a normal distribution. If it is not following, then it is not very good. Okay. And as I said, I will teach you how to check whether the data is normal or not normal later on. There are some tests for that. There are many tests later on for non-normal distributions also. Okay. So, in that data, the null hypothesis could be sigma 1 square is equal to sigma 2 square. The test statistics could be S1 square by S2 square. Okay. And then numerator degrees of freedom is n1 minus 1, denominator is n2 minus 1. Okay. So, if I have two sets of samples, n1 is 11, n2 is 16, S1 square is 6 and S2 square is 3. So, the ratio test statistics F will be 6 by 3, that is 2, and then F value I am looking at 11 and 16, that means 10 and 15 for alpha is equal to 95%. So, 10 and 15. So, what is the equation, sorry, what is the table? 10 and 15 will be here, 10 here, 2.54. Okay, the numerator is 10, denominator is 15 degrees of freedom. So, I put it as 2.54. So, F is equal to 2. Obviously, the calculated F is less than the table S. So, do not reject the null hypothesis. Okay. Please remember, these F values are for one tail, okay, only the right tail. So, if you want, it is only for the right tail. Okay, so, it is very simple. We need to use this table, and from the table, just like t test, we calculate F value, and the F value calculated is less than the table F value. We do not reject the null hypothesis. Now, this Excel function is also there, that is called the Fdist function. Okay, so, we give the probability, the value. Okay. So, Fdist gives you the probability that the F distribution is df1 and df2 degrees of freedom. This gives you a cumulative actually. Okay. So, we will give the F value, we will give the degrees of freedom, and it will give you the probability. For example, let us take this particular problem. So, it will be 2, 2, 10 and 15. So, let us go to F distribution. I will show you in the Excel also. Okay. So, let us look at the previous case as such. Sorry, we will say Fdist, 2 is my test statistics, degrees of freedom is 10, okay, comma 15, these are the 10 is 1, 2 is my F statistics, 10 and 15 are the numerator and the denominator degrees of freedom. Okay. So, it gives you my p value, okay, that is 0.10914. Okay, that is what this F distribution gives. Sorry, yeah. So, it gives you the probability value. Okay. So, it gives you the pre value. Obviously, P is 0.109, which is much very large. So, obviously, we reject the null hypothesis. Okay. So, this Fdist function in Excel gives you the p value. Now, there is inverse, F inverse is also there. Okay. Okay, F inverse. So, it gives you the value of x such that the right tail of the distribution will have an area of alpha. Okay. So, basically it gives you the inverse of the F probability distribution. Okay. So, it gives you, so you have the degrees of freedom here, degrees of freedom here, okay, and it will give you the, given the alpha, okay, it will calculate what will be the, okay. So, in this particular problem, if I say F inverse 0.05, 10 and 15, okay, it gives you 2.54. Okay, see, it gives you this. So, for a p is equal to 95% or p is equal to 0.05. So, whatever that table is giving, So, it will give you 2.54, okay, 10 and 15, as I said 10 and 15, okay, 10 and 15, sorry 10 and 15, 10 and 15, it gives you 2.54. So, I use the finv function. So, I can use the finv function to calculate the value exactly the area exactly just like the table. So, here I will mention the probability 0.05, whereas the Fdist will give you the probability where I will put the ratio here 2.54 here and then or 2 here and then put the degrees of freedom here, okay, 10 and 15. Okay. So, I can use Fdist which will give me the area or the probability, or if I want to given the probability it will calculate the f value using fin function. Okay. So, we can use both either the Fdist or fin, both are quite good. So, this can give. So, fin it gives you the probability, okay. That means if it will calculate the probability, and if the probability you calculate is less than 0.05, we can reject the null hypothesis. So, you use this particular thing, or we use the Fdist, it will calculate, okay, it will calculate the area under the curve. Okay. So, in case there is large amount of variance due to chance, it will lead to a smaller F ratio. Of course, as you know, numerator denominator, if the denominator variances are very large, obviously the ratio will become small, so the F ratio also will become small. So, there will not be any significance. So, what does this statement mean? Suppose I am an operator, I do repeat the same sample 4 times or 5 times, and each time I get large variation. Obviously, my variance will be very large, okay. Whereas I take an expert operator who repeats the same sample 4-5 times, his variance is okay, is not very large, it is very small. So, if I am dividing one by other, I will get much difference. So, if the variances are very large, I am going to get a much smaller F ratio. So, I will not be able to differentiate between 2 sets of drugs, for example, or 2 sets of instruments, for example. So, if the repeatability is good, then if there is some variations between sample 1 and sample 2, then I will be able to see the difference. If the experimental errors are very large, then I will not be able to see variations between sample 1 and sample 2. That is what this particular statement is all about. That means, if I am doing experiments, the variations in my experimental measurement should be very less. With more random variation, the patterns could actually be due to chance. Okay. So, if there is a lot of variation, it could be just greater the difference between the groups, okay, then the easier it will be to find a difference or pattern despite random variation. So, if the variations are very large, okay, then you may even if the variations because of error or chance or random is large, you will be able to find differences. But if the variations between 2 sets of samples is small and the variations repeatability is large, then I will not be able to do, because my F ratio will come out very small. So, larger the F ratio, better to find a significant effect. So, if I am comparing 2 sets of drugs or 2 sets of instruments, so I need to have a larger F ratio. Okay. So, my variations repeatability should be very less. That means, within sample error should be very less. So, I am introducing a new word that is called within sample error. So, within sample error should be less, whereas between sample, that means sample A and sample B, or instrument A and instrument B. So, that is called between sample variance, whereas within sample variance means variations in the repeatability. So, one is called between samples, that is A and B, instrument 1, instrument 2, operator 1 and 2, that should be much larger than within sample error, that is called the sampling error or chance error or random error. So, between sample versus within sample, that is what you are trying to do in F ratio, and it is very powerful because we can use this for comparing, like I said, 2 drugs or 3 drugs or many drugs, 2 operators or 3 operators or many operators or many instruments, sample done in different locations and so on actually. So, always we should have less variation within sample to see a difference between samples, that is a very important statement. So, a very large F value means that between group variance surpasses the within group, you understand, between sample errors variance within sample variance. Always within sample variance should be very small in order to find between sample variance or between group variance. This within sample variance is also called error variance, whereas between sample or between group is also called effect variance. That means effect is I am comparing between drug A and drug B, temperature of fermentation at 30 degrees and 40 degrees, fermentation at pH of 3 and 4. So, if I want to see a real variation, statistically significant variation between pH at 3 and 4, when I do a repeatability, those variations should be much smaller, then only I will be able to see a difference between effect, that means pH 3 and 4 or temperature 30 and 40 or drug 1 and drug 2 or operator A and operator B. So, within sample variance should be much smaller than between sample variance. That means I should have a good assay method, I should have good instruments so that the errors when I repeat are much less. So, this is a very key in Ftest. In fact, it is a very key in many studies where you are comparing samples, comparing drugs, comparing operators, comparing assays, comparing instruments, comparing bioprocesses, comparing yield of plants and so on. Okay. The p value gives how likely the obtained F value is going to occur. P value we can use this okay, Fdist, that gives you the p value. Okay. We can use Fdist function where x is the ratio of the variances, df1 numerator and denominator. So, the p value gives how likely the obtained F value is going to occur. So, if the p value is greater than 0.05, then we will say it is not a greatly significant. If the p value is very small, we will say it is greatly significant. Okay. So, we can use the as I said Fdist function in Excel to do this particular job for you. Okay. Okay. We can also use the GraphPad software. So, as you can see here, it gives you the F value. Okay. So, we can say calculate, continue. So, here we can say calculate p value from F or calculate F value given a probability. So, as you can see Fdist and F inverse both can be done here. Okay. So, we can say here for example, so F ratio, so we give a probability say 0.05 and then the degrees of freedom 10 and degrees of freedom 15 in that problem, compute F value. So, you see 2.543, it gives you a 2.543. Okay. So, we can, that is equivalent to your F inverse. So, if we want to do Fdist, then obviously we use the other here. Okay, here what do? We give the F value and then this will give you the probability value equivalent to Fdist. Okay. So, it gives you 0.1091, understand. So, we can use both these functions in this software. So, this gives you the exactly whatever the Fdist function gives you, it gives you the probability value for given a F ratio and degrees of freedom, whereas this one gives you the F value. Okay, when I give the probability of 0.05 and the numerator degrees of freedom and the denominator degrees of freedom. Okay. So, we will continue on this F distribution further in the next class also. Thank you very much for your